Welcome you all for the third session of air standard cycles. In this session, we are going to discuss about the problems on Otto cycle. Let us discuss one problem. A 4-cylinder, 4-stroke. கட் பண்ணிக்கலாம் போட்டுங்க. A 4-cylinder, 4-stroke SI engine working on Otto cycle has 250 mm bore and 375 mm stroke. The clearance volume is 0.01052 meter cube. The initial pressure and temperature are 1 bar and 47 degrees Celsius. The maximum pressure in the cycle is limited to 25 bar. Determine thermal efficiency of the cycle and mean effective pressure. So this is the problem that we are going to discuss now, and let us write the given data first. Given data, the number of cylinders 4. The number of cylinder is 4K, and the diameter of the cylinder, that is bore is 250 mm, and stroke is 375 mm. The clearance volume is VC, that is equal to V2, is 0.01052 meter cube, and pressure at the inlet is 1 bar, at the initial stage is 1 bar, and temperature, initial temperature is 47 plus 273, 320 Kelvin. The maximum pressure in the cycle is Pmax, that is equal to P3 is equal to 25 bar. And now we have to find case 1 thermal efficiency of the cycle, and case 2 is the mean effective pressure. So we have to start with some assumptions. The assumptions are: air is used as the working medium, hence gamma is equal to 1.4, Cp is equal to 1.005 kilojoule by kilogram Kelvin, and Cv is equal to 0.718 kilojoule by kilogram Kelvin, and R is equal to 0.287 kilojoule by kilogram Kelvin. Now we have to solve this problem. Solution. Before starting a solution, let us draw the PV diagram. So the PV diagram, if you draw the PV diagram, this is the PV diagram. The process 1 to 2 is a compression process, and 2 to 3 is a constant volume heat addition, and 3 to 4 is the isentropic expansion, and 4 to 1 is the constant volume heat rejection. So here the process is PV power gamma is equal to constant. Here the process is PV power gamma is equal to constant, and here the heat is at process 2 to 3, the heat is added, heat is supplied, and in process 4 to 1, heat is rejected. So this is the PV diagram. Process 1 to 2 is a compression process, isentropic compression. 2 to 3 is the constant volume heat addition. 3 to 4 isentropic expansion. 4 to 1 is the constant volume heat rejection process. And here this is the clearance volume Vc, and this is the swept volume Vs. Okay, and this is also equivalent to V2, and this is equivalent to V1. So now we have to solve this problem. To solve this problem, let us start from here. The case 1. Case 1 is the thermal efficiency of the cycle. Thermal efficiency of the cycle. And in this one, we have to find out thermal efficiency, for which we need to find first compression ratio. So let us start with the compression ratio. To find the compression ratio, we need swept volume. It is equal to pi by 4 T square L into K. So pi by 4, D is actually a bore, which is 0.25 the whole square, and L is a stroke, which is 0.375, and number of cylinder is 4. So you will get pi divided by 4 into 0.25 square into 0.375 into 4. So you have 0.07363 meter cube. This is Vs. Now we have to find out V1. V1 is equal to Vc plus Vs. V1 is equal to Vc plus Vs. We know Vc, which is equivalent to V2, therefore 0.01052 plus 0.07363 is equal to, so 0.01052 plus 0.07363, you will get 0.08415 meter cube. This is V1. Now I have to find out what is the compression ratio R, that is equal to V1 by V2. The compression ratio is V1 by V2. I know V1, volume at initial stage, entry 0.08415, and this is the volume after compression So I'll get the ratio like this: 0.08415 divided by 0.01052. The answer is approximately 8. So compression ratio is now 8. Once we get compression ratio, then we have to find out the thermal efficiency. The thermal efficiency of an Otto cycle is equal to 1 minus 1 by R power gamma minus 1. So we know the compression ratio is 8, 1 by 8 power 1.4 minus 1. So we get now the answer as, so 8 power 0.4, so it's 56.5647, that is equal to 56.47% is the thermal efficiency. Okay, so this is the one answer we get. Now we have to find out the case 2, mean effective pressure. For finding mean effective pressure, let us start with finding out the temperature after compression. So after compression, the temperature is T2. I have to find T2. T2 is equal to T1 into R power gamma minus 1. So that T1 is the value, T1 is 320 Kelvin. So 328 power 1.4 minus 1 is equal to 320 into 8 power 0.4 is 735.17 Kelvin. Then we have to find out P2. P2 is equal to P1 into R power gamma. So what is P1? It is 1 bar. So 1 into 8 power 1.4, which is equivalent to 18.38 bar. Now we know P3, maximum pressure in the cycle. Then we have to find out P3. T3 is equal to P3 by P2 into T2. This is the formula, because the process 2 to 3 is a constant volume process. For a constant volume process, we get the PVT relationship as T3 by T2 is equal to P3 by P2. From this, we can find T3. So we know T3, we have to find T3. Then P3 we know, which is 25 bar, and P2 we know it is 18.38 bar, and T2 we know it is 735.17. So we get now 25 by 18.38 into 735.17 is 999.96 Kelvin. So then we have to find out mass flow rate, mass of air handled per cycle. So M is equal to P1 V1 by R T1. P1 we know it as 1 bar. I can write in terms of 100 kilopascal into the initial volume, which we have found out here as 0.08415 meter cube. So that I am substituting here, 0.08415 divided by R, the gas constant, which is 0.287 kilojoule per kilogram Kelvin. Since I am substituting P1 in terms of kilopascal, I am substituting R in terms of kilojoule per kilogram Kelvin, into the temperature T1 as 320. So now if you calculate these values, 100 into 0.08415 divided by 0.287 and divided by 320, you get 0.0916 kilogram of air. Okay, 0.0916 kilogram of air we get for mass. Now what is the heat supplied? So heat supplied, Q heat supplied is equal to M into CV into T3 minus T2. right? So mass we have found out as 0.0916, CV it is 0.718 kilojoule per kilogram Kelvin, and T3 we found as 999.96, and T2 it is 735.17. So we get the heat supplied as 0.0916 into 0.718 into the difference between 999.96 minus 735.17. So I get now 17.42, 17 point, we can write even 415 kilojoule. So this is the amount of heat supplied. Now I want what is the work done. Why I am finding work done? Because mean effective pressure is nothing but the work done by swept volume. So I am finding the work done. So work done is equal to heat supplied into efficiency of thermal cycle. So now I substitute heat supplied, which is 17.415 into the thermal efficiency. I get as 0.5647. So this value I am substituting here, 0.5647. So I get now 17.415 into 0.5647 is equal to 9.83, 9.834 kilojoule. And then I have to find out the mean effective pressure. The mean effective pressure now is equal to mean effective pressure is equal to work done by swept volume. So work done is equal to, we have 9.834 kilojoule per kilogram, kilojoule, 9.834 kilojoule. So 9.834 kilojoule divided by the swept volume. We have found out here it is 0.07363 meter cube. So 0.07363, I get now 9.834 divided by 0.07363, which is 133.56 kilo Pascal, or I can write 1.33, I can write 1.34 bar. Okay, so this is the mean effective pressure. This is the mean effective pressure. Right, 1.34 bar. So we have now found out that the thermal efficiency as 56.47 percentage and mean effective pressure as 1.34 bar. If you see here, the temperature at the end of the compression is more than at the inlet because it is isentropic compression process, and the temperature at the end of heat addition T3 is more than T2 because during the process 2 to 3 the heat is added at constant volume. So naturally the temperature at third state will be more than the second state. Right.
திருப்பி கண்டினியூ ஆகும்.
இப்போ